But the other thing I'm keen to understand, and I have been working on for some time, is how to reconcile quantum physics and gravity. This has always been a passion for me, and just about every other theoretical physicist thought about it for more than 10 seconds. We're now at the stage where we can control states of matter and states of light, that we can begin to think about how gravity might change quantum effects. So if I have a superposition of a particle in two different places, what is the gravitational field of that particle? Is that a sensible question even to ask? More particularly, coming back to my discussion of the measurement problem, where I try to suggest that it's the space-time coordinates of the apparatus that matter most, and that implicitly makes an assumption about gravitational fields. Is there a path there to understand what new experiments we could devise that would give us a hint on how gravity and quantum physics should be put together? I should preface this by saying that people have been trying to reconcile quantum physics and gravity since Einstein, well, shortly after Einstein invented general relativity, which is our modern theory of gravity. No one has succeeded in explaining any experimental or observational data yet. There are some beautiful theories which may yet turn out to be heading in the right direction. One is loop quantum gravity, associated with many different people, but Carlo Rovelli particularly.
I've read his book Order and Time.
Yes.
I definitely got very confused.
It's a beautiful book. Yes, yes. He writes in a very sort of poetic style, which is inspiring, but perhaps to understand it requires a little bit more technical language. So, and the other one is string theory, of course, which is what happens if you push quantum field theory to the extreme where you'd like to explain gravity. But so far, neither of these, I mean, they both feel perfectly consistent mathematical theories, but there's a lack of any experimental evidence as to which way we should jump, or observational evidence for that matter. One of the big puzzles and probably big hints as to something that's going on is the cosmological constant problem. As we know, the universe is expanding, but the expansion is accelerating. It looks like there's some sort of anti-gravity stuff pushing it apart on a cosmological scale. It's consistent with Einstein's theory of general relativity if you put a term called a cosmological constant into his equation. So you say, well, where does that come from? Well, if you say, well, maybe it's due to quantum fields, maybe it's just due to the vacuum quantum field that's floating around out there all the time from all these sort of ground states of various fields, electromagnetism, strong nuclear force, and so on. Say, okay, maybe it's due to the vacuum energy. You work out what the cosmological constant should be, and you find that you're out by a factor of about 10 to the 120 or something, some absolutely phenomenally bad prediction. So there's this question of what is this thing we're seeing that we interpret as cosmological constant? Does it have a quantum origin or not? And if so, what does it tell us about a quantum theory of gravity? I have some ideas on that. I'm working with my PhD student, Francisco Pippa, on this, and a student at Oxford, Pranav. We have some ideas. I've been involved in the theory of various experiments to test this with Sagata Bose at University College in London, where some years ago he and I and many others came up with an experiment to definitively tell us whether or not gravity should be quantized at all. Maybe gravity's not the sort of thing you quantize. It might be like the equation of state for an ideal gas, PV equals NKT. I mean, it's correct and it describes the physics, but you don't start out by trying to quantize it. If you want a quantum theory of gases, you do something completely different. Gravity might be like that. That would be puzzling because the way Einstein formulated it can be reformulated as a regular old Hamiltonian field theory, which we've been able to quantize in the past quite successfully, but so far failed with gravity, except in a very approximate so-called linearized sense. So this is something that occupies me more and more, is this question of reconciling quantum physics and gravity.
Okay. So, you mentioned we have a quantum loop gravity.
Yep.
You mentioned string theory.
Yep.
So, tell me if I understood correctly. We have certain, well, we have the development of quantum physics in this 20th century that suddenly makes us question our initial understanding of what gravity is. And thus we're trying to come up with a better theory that explains gravity that makes it work within quantum
Yes.
physics.
Yes.
And these are, so can you explain us a little bit, and then I want to go a little bit into quantum Turing machines too, as you're working on them. Before we get into that, what are some of the differences, and explain us a little bit the different predominant theories now that are being developed to explain gravity.
Okay. So one idea, due to Roger Penrose and Las Diossi, is that whenever you try to make a strange gravitational field by taking a source, like a chunk of matter, and putting it in a superposition of two different places, say, the minute you try to do that, gravity will guarantee it will collapse into being on the left or the right, but gravity will really, in essence, measure where the particle is and localize it. It's called, well, it has various names, but Roger Penrose calculated a rate at which it should happen, which is determined by the self-energy associated with the distribution at the superposition. There's something really strange, and his intuition behind this is that when you have a lump of matter, the gravity, if it's just, actually it's a little bit difficult to talk of a lump of matter alone in the universe. That makes no sense from a gravitational point of view. So let's suppose a lump of matter in a laboratory. And so I have a reference frame where I know where it is in relation to everything else. In other words, I know where it is in relation to a background gravitational field. If it's in, so for sure, if I let go, it'll fall in a gravitational field and it will move on a geodesic. And that geodesic is unique. Its entire past and future is fixed by the gravitational field of the universe. But if it's in a superposition, the geodesic is not unique anymore, so it's clearly inconsistent with general relativity. Another way to state it is the gravitational field of that mass is not stationary. It would look as if it was fluctuating between being on the left-hand side of the laboratory or being on the right-hand side of the laboratory. And that's a very strange notion, that the gravitational field should be noisy and stochastic at that level. But just the mere fact that the notion, in fact, you can cash it out this way. As I said earlier, quantum states the position and trajectories of particles, in a sense, don't exist unless you measure them. If I have an interference experiment between source and detector, if I don't put any detectors in between, in a sense, particles take all trajectories. That's what Feynman described it. But we know in each trial, you have one particle at the source and you get one particle at the detector. There was only one particle in the system, clearly. At least that's what you'd like to claim, given you only detected one particle. But to give a trajectory to it between source and detector is going too far. But that's clearly inconsistent with general relativity, which says that between source and detector, that particle was on some sort of geodesic, at least until it interacted with the source and detector. And so there's no way to assign a unique geodesic to a superposition of paths. And so this is part of the problem, that there's no consistent way to combine our description of the quantum world outside of classical trajectories in terms of the world of general relativity, where objects move on geodesics unless they interact with non-gravitational forces.